So we are just waiting for the other guys. Just started. Yep. So Sigi, I made you the co-host, and you can add everyone when someone's coming in.
Yeah, thank you.
So hi everyone, my name is Raghu, and welcome to the Wastewater Talk. So we do it every week, every month on the first Thursday. We make one episode with different kinds of topics which we are facing in the wastewater treatment, and we can also share our knowledge and exchange our knowledge in different countries internationally, like what are the solutions for the wastewater which we are facing with the problems and everything. So and my name is Raghu. I want to introduce about myself first and go again with others. So my name is Raghu. I'm from India, and currently I'm living in Germany, and I'm working as a project engineer in the company Unitechnic. And today we are going to discuss about our sulfate balance, and then I'm going to give. Today we have a co-host speaker, Professor Wollaston, and he is also going to explain a little bit about his inputs and his knowledge and his process and model which he's working on. So next, we would like, Sigi, would you like to say something for the group, like introduce yourself, you and Klaus, and talk a bit?
Yeah, sure. So me first or you first?
Ladies first.
Okay. Okay, so hello everyone. My name is Sigi Tong. I come from China and studied water resources engineering in Germany. And yeah, now I work as a project engineer at Unitechnic. And I'm also the co-host of this wastewater talk. I do the morning session, and Raghu does the afternoon session. And I'm interested in the wastewater treatment and management technologies that has been used in other countries. Or yeah, I would like to hear the sharings from our participants. Thank you.
Yeah, my name is Klaus Jirk. I'm the colleague of Sigi, and I'm also interested in what you guys have to say. Regards wastewater and especially odors, and today especially, and what your experiences is there and so on. So we are a small group, so we have a very intimate discussion later, and I'm looking forward to your insights. Thank you.
So Professor, can you please introduce yourself for the new members who are not there in the morning?
My name is Jes Wollaston, and I am a professor of environmental engineering at Aalborg University. I have worked with chemical and biological processes in sewer networks since the mid-90s. And I have the university I'm working on has been the host of developing the process concept that is today used for simulating chemical and biological processes in sewer networks. I also do consultancy on sewer processes and so on, but I will talk a little bit more about that during my speech. Yep, that's about it.
Thank you, Professor. Mr. Isa El Amal, right?
So
yes, sorry if I'm wrong.
Yeah, no problem.
Can you introduce yourself? I'm sorry for the mispronunciation.
No worries, no worries.
Can you introduce yourself to the group, please?
Yeah, of course. Yeah. Okay. So I am Isa El Amal. I'm Moroccan. Actually, I've worked like in 5 or 6 years with a water distribution and wastewater management utility in Morocco, in Casablanca region. So I'm really interested in that field, like in wastewater treatment, wastewater management, all this. Currently, I'm in Germany, Cologne. I'm doing my master in TH Cologne. Like it is about water management. And yeah, that's all.
Welcome to Wastewater Talk. And
Thank you so much.
yeah, and Monica Singh. Hello, can you hear us? Hello.
Hello.
Hi. Can you introduce yourself to the group, please?
Yes, sir, sure. Sir, Monica this side from India, and I am the technical salesperson, and we are in the manufacturing of bacterial bioculture for the wastewater treatment. And we specialize, we manufacture specialized bioculture also for the removal of ammonium nitrogen and for the proper generation of MLSs. So yeah, like we are into the wastewater treatment field.
Welcome to the Wastewater Talk, Monica.
Thank you, sir.
So next we have Ehsan Sabeti. Can you hear us?
Yeah, I'm here. Thank you for invitation. And I have a problem with this. Okay. And this is Ehsan. I'm Vice President of Operation, Water Operation and Sewage Operation in the city in Iran. And my bachelor was about water and sewage network and treatment plants, and my master was about water resource management. And I'm working for 12 years in this field.
Nice. I think you are already in the Wastewater Talk, right? I remember you seeing in the other episodes as well.
Yeah.
Okay, welcome back again, and I'm happy that you're back.
Thank you.
And we have the last one, Petar. Sorry, she's gone. Okay. Yeah. Anyways, if anyone is joining later, they can write in the description in the chat box. So first, I will give you a short presentation. I mean, we made a short presentation, me and Siggy, about the sulfate balance today, and then I will give the mic to Professor Wallerstein. So moving on, I will share my screen. So sorry. Just a second. So you guys see the presentation?
Yes.
Okay, perfect. So welcome to the Wastewater Talk, and as we see, this is our episode 7, and every month we are doing one episode in the first week of the Thursday. So myself and Siggy and Klaus, we are the participants and co-hosts. So I want to just go on an introduction of what's Wastewater Talk and everything just before we start. So it's like we come on with a new topic every month, and we discuss more about it, and we exchange the knowledge in wastewater. We wanted to know how it's going on in Germany and Europe, and we don't know anything about the other countries, like in the other side of the world, how it's happening and what are the solutions they are using. And from April, we started to have 2 meetings in 2 different time zones, because not every person lives in the same time zone. So if you are in America on the one side of the world or the other side of the world, so it's better to have more time zones so that you can connect more people. That's so if you have a passion to share, and if you want to know other technologies or other persons, and this is the right place for you, like I would say. And here it's about the Wastewater Talk. It's the link to our website, and you can just see all about it. And moving on, so today the topic is, as you see, today is the 7th episode. It's sulfide balance in our drainage systems. So I wanted to talk a bit about that. And so first, I want to show you about the company. So our company is Unitechnics, like I said, and it started in 1990s, and then with the engineering products and this engineering work. And since 2000, we started to develop the projects which will eradicate or reduce the reduce the sulfide in the sewers and increase your sewer health, life, and everything. So moving on that, and yeah, like I said, these are some kind of projects or products which we do, like engineering consultancy, and we also do indirect discharge, and we have a drone which is doing the sewer system inspection, like one of a type in Germany, more like using drones in the canals and seeing the controlling and see how the sewer life is without sending any any labor in the sewer, so that you minimize the risk of contact. And we also do sulfide balances, which is this episode is about, and we also have preventions and products, like I said earlier, about the odor and the corrosion in the sewage canals. And we also have something for external water seal, which prevents the rainwater from precipitation coming into the sewers and overflooding them. And we also have dosing technologies for exhaust air treatments for the canals, which we use chemicals, and we also use activated carbon, which was last episode, by the way. And we also have some products to fight the rat problems in the sewers. So moving on. I wanted to say why the development of why this problem has arisen recently. Like in the previous times, the water consumption was so high in Germany. So it was around 150 liters per day and per person. And now it gradually, as you see in the chart, it's like gradually decreased to 122 liters per day per person. And it's not so much as before. Because of this reduced water, the water stays more time in the sewers and in the pumping stations. And decreased water consumption and wastewater generation is like is leading to other problems, and it creates long retention times, like the residence time in the sewer systems, which forms more hydrogen sulfide, which has a more chance of hydrogen sulfide. As you can see in the picture, in Germany, every manhole has this holes, manhole cover, has these small ventilation holes, which we call, so that you get the more oxygen level. But these manholes are also leading to the emission of odor from the manholes, and which leads to several complaints and unpleasant environment for people to roam around the streets or live nearby to the stinky manholes, and can't have a pleasant and a happy time. So that's all. That's the complaints from citizens is like the most concern for the water treatments as well. So, and we also have a typical problem in Germany, like you see here, the formation of sulfur into the hydrogen sulfide, and this has a long resistance time, like I said, and because of this high time in the sewers, it creates so much fouling smells and corrosions for the concrete, which because it reacts so hardly and so fast with the concrete. So due to this reasons, many municipalities in Germany are spending way much more money for the sanitation of the sewer pipelines than before. Once upon a time, they used to have a life of about 20 to 30 years or even more, and now they are like rapidly corroding because of the high hydrogen sulfide levels. So what we do in our company is we used to manually, once upon a time when there is no computers and technology, we used to manually do it everything by hand, and we do so many formulas and so many tables, and it's so complicated work to do the sulfide balance, and it takes a lot of time. So now what we did is we technology upgraded, and so we want to upgrade the technology even in this wastewater field, like making more digital. So we made all these formulas and calculations, and then we started a new program which is called Sulfide, and you can see the elephant. So this is kind of a symbol of the software. So you put all of these tables, and then you can just give the software. So it's like the basic easiest version. So what does Sulfide does? So it makes the digitalization of the drainage systems. Like once upon a time, you like I said, you send people into the manholes and sewers and just check the problems what they're creating. But now we have many new options, and like simulation. It's simulations in different complex products and the different situations, and it also calculates how much oxygen consumption and how much is the hydrogen formed in the thing, and you have a nice overview of what's happening, like a visualization. Like it's better to have a very uncomplicated, and we can see basically everything like with this software. So it also identifies where it has a higher level of odor emissions and how the corrosion is, so which places has high, stronger corrosion levels, so that the wastewater engineers and the canal planners can use it very well and then have a better result in a fast way. So it also optimizes for the operators and planners. And I just want to go quickly through the workflow. As you can see, first step is always analyze. Like we have to access the data. Every wastewater municipalities have their data, like raw data, such as how much is the COD levels and how much is the basic data, how much oxygen consumption and how much is the pH level and what is the temperature in the sewers. They are always kept in a record by every wastewater treatment plant. So we get those parameters, and then after that we do the modeling. We track the emission, and then we see what are the potential damages, what can be done. And after that we do the options like comparisons, which measurement will be useful for which kind of problem. Like we can't use every same answer for every situation and every question. So we have to calculate it, and we have to have so many variations, and then we see which one is most effective. And then we get the results, like we see how much the cost and how much we have to invest, and we need to take the time and what is the best ideal way. And then at the end we do the implementation after we get the go, and this is how the workflow with Sulfidos is. So like I said, this is the first Sulfidos interface. It looks like it's just a screenshot of the Sulfidos software. So here you can see, here's the map of a city, which is directly extracted for just like a Google Maps, and it's clearly stated which interface, same like Google Maps. Like you can have street names and all the streets and the housing plan exactly, and the water bodies and the river basins, so that you can have a nice overview of the city, of the place which you want to do the sulfide calculation. So here you can see the zoom function. You can zoom in and zoom out, and these four are the arrows which you use. Like this is actually a freehand drawing. You don't need to you operate it as a CAD, like giving the dimensions, and it does the work and length and everything. You just draw it by hand, like like you do with your iPad. Just draw with a pencil. In this we used with the mouse, and then we connect the dots. So we form this kind of line. And then these four are for four different purposes. One is used for the pressure pipeline, and one is used for the wastewater pipeline, and one is for the gravity sewers, and so on. So, and you can see it has three toolbar, like it's data, and it's like you have to give your data and everything. You have to give your inputs, and then you have to give the sewer lines and COD values, and then it shows the results of it. Like you can see, if you click this eye icon, and then it turns the colors, so that you can see where is the higher and lower concentration of the hydrogen sulfide. And after giving all the inputs, you click this elephant here, and this symbol called Sulfidos, then you get the calculation in kind of minutes, in seconds to minutes. Like it depends upon how high the calculations are. And you can zoom out and zoom in, and you can choose the location with this location icon. Just give the coordinates of the place which you want to do. If it doesn't have a particular address, you can also give the latitude and longitude, and it automatically takes the map from there. As you can see, these are the data which I'm talking about. Like you have to give this basic data and this additional data, and then you get the results. So hydrogen sulfide, or like how much hydrogen is there and how much oxygen consumption it did and everything. So this is typically the Sulfidos, which is a test phase. And here you can see, like I said, the color coding. So the green is like the good quality, and you can see if you are a planner and if you are seeing some picture like this, then you know, okay, so this is the area where you have to concentrate about, and this is the area it's free of sulfide and smell. So you can check how much is the pipeline which is corroded, and you can then decide what kind of measurements you want to do. So it's color coded like in green to red, and green is good, and red is like severe, and it's moderate to low. And these are the solutions which we offer to the after the sulfidus. Like sulfidus is like the first part, as we see in the table, like it's like the analysis part. And after that, we give different kinds of further solutions. Like for example, we always use the chemical dosings of iron, because iron and sulfide do a better combination, and they can be stable. And we can also use nitrite and iron, and sometimes we also use compressed air flushing, which is very costly and very noisy, but it's also an idea. And we have something like this manhole filters, like it's a temporary prevention, which can be reduce odor with a hydrogen activated carbon filter, which is fitted in, and you can just install it in the sewer, and then you can prevent the odor from the citizens and have a redemption. I mean, for temporarily. And after that, I want to show you this small video which we made in the company. Here you can see how the manhole covers in this hose. It's emitting the odor, and it's starting to get stinky phase, and it starts to emit the odor into the environment. So you can see this is the manhole shaft, and here it's made with actually with concrete. So this is the pumping station on your left, and it pumps with a pressure pipe, and then this goes into the gravity sewers. So when the manholes are there in near to your household, it starts to stink. And in the summer times, when the temperature is so high, it starts to stink more, and then is the time where you get more complaints from your from the people to the municipalities and everything. So there is this chart like which has a projectile which shows that hydrogen sulfide like starts slowly and then picks up its trend. Like this is just a picture saying that it's like once upon a time we used to have more water, and now it's like very less water consumption. So, and then as you can see, this is the first manhole. Like you can see how the corrosion is building up in the sewer, which reacts very fastly with concrete, because concrete mostly people use concrete because they have the better structure, and they have the structural stability. So that leads to corrosion as well because of the wastewater which is projected. And you can see here the street. You can also detect in your house and everywhere in the parking place, and near to the water body and near to the rainwater canals and everything. So it's like stinks everywhere. So what did we do is we did the calculations, and we put everything like this kind of maps, which makes easier for the companies to project, so that it saves more time than doing it manually. So it's all calculated process and a simulation. So it also says which temperature it is, and it depends on the day of which year. Like in Germany, it's very cool in winter, and it has a huge difference. So that's how this sulfidus works. And yeah, so now I wanted to know, like this is on our part, and now I wanted to give the opportunity to our guest speaker today, Professor Wollaston from Aarhus University, with us, and he wants to explain his model he's working on.
Yep. If you want to share that. Okay. Who's disabled participant screen sharing?
Okay, so I start my screen sharing. So
No. Somebody has to just to allow screen sharing. I don't know exactly.
Raghu, I think you need to give Professor Wollaston also the co-host.
You make him the co-host, and then
okay, sure, yeah, perfect. Just a sec. So yes, now you can, sir.
Now it works. That's fine.
Yeah.
Oops. Let's see. That was probably the wrong thingy.
It happened to me too. Yeah. The same thing happened to me. Like I have like 4 presentations open, and then I got confused with one with the other. So it happens.
The one I just was studying percent was in Danish, and you probably didn't want that.
Well, hopefully nobody understands Danish here. So
hopefully, yes, exactly. probably not. No. So what I'm going to talk about was mentioned already is sulfide and sewers. And the work regarding sulfides and sewers started in Aalborg University around 1983, when my predecessor in the professorship I have now started on looking on transfer rates of oxygen in sewers, because if you don't get your oxygen balance right in the sewer system, you don't get your sulfide balance right. So we have been at it for, oh my God, for 40, 50 years or something like that in Aalborg, meaning not necessarily me all the time, but my predecessor and then me and my group and my research group. And we have in Aalborg over the many years developed a lot of research knowledge on what actually goes on in the sewer systems. Sewers are horribly complicated. So each small detail is the work of a PhD, sort of. Okay, let's come back to that. But first of all, nobody, maybe excluding the present audience, loves her sewers, right? The public does not want to know about them, right? It's annoying. They definitely don't want to see them or the wastewater. They for sure don't want to smell the stuff. So what the public want is to ignore the existence of the sewers. On the other hand, they definitely want the services. So they want the sewers to function without any interruption and any fuss, without thinking about that. People always start laughing when you talk, when you tell you're working with sewer systems, and they don't quite know what to say and so on. That's the way it is. So what we have to do is make sure this service function and without the public actually noticing it. This is I heard we have had one guy from Morocco, and this is very interesting. He might recognize the space. This is Tangier in Morocco, where I back in, what was it, 2012, 13 or something like that, did a study on odor issues in the city. And what you see here is a super nice place, right? It really looks beautiful, doesn't it? So you have the beach out here, the sun is shining, and there's a lot of nice boulevards here. But why are there no people? Why are there no people at the beach? Why are there no ice cream stands here? So why not? I mean, my personal theory, without having it proven in terms of full scientifically proven, is that it stinks. It stinks of sulfide along the whole boulevard, because down here in the street there were 3 or 4 main interceptors running in parallel, and when you lift the manhole covers, it looks like this: corroding concrete, corroding mortar, things falling apart, quicksand water, still standing water down here, right? So that's probably why there are no ice cream stands and no coffee shops. So the whole business of this very nice sites, and very touristic sites, becomes inhibited, becomes damaged by this issue about the sewer odors. And we were at that point in time modeling it. This was we didn't have a super good hydraulic model, but we had a sufficiently good hydraulic model for this, and we modeled what happened here. And this is pipes with more than 100 ppm in the gas phase, and this was actually the boulevard you saw here is down here at the coast. So we worked on solving those issues for them, or at least identifying the problems. That's better to say that, because modeling doesn't solve anything. Modeling just shows you where you might have problems. But of course, Tangier is not the only place where you have problems. This is an example from the US. It is San Francisco in California, where I did my first large study in the USA. And this was initiated by the citizens of San Francisco complaining about it stinks of sewage. And the place, and then the utility tried to do something about it, putting in these ventilator shafts here, which didn't work at all. And it was a lot of political noise due to this. Actually, if you go down the street in San Francisco, it doesn't smell very much. But if you are sitting at the Embarcadero, at the very expensive cafes, looking at the tall ship race and so on, and having your cafe latte, and there comes a whiff of sewage, it's not good for business, right? It's really not good for business, especially if you're talking to, if you have rich tourists in the area. So what San Francisco wanted was to get a grab on the problem. What we then did back in 2014, 15 or something like that was simulating all of San Francisco. There's two catchments. This is the Bayside catchment you see here, the largest one. And then identifying where were the issues, identifying solutions, what to do about it. About odors, this is really a funny thing, right? Because it's not the stink itself that matters, but it is the bad smell at the wrong place. This is a picture, a Google Street View picture of the treatment plant in San Francisco. And if you go there, it really stinks. Oh my God, it stinks. But it doesn't matter, because this is a very, very poor area. There are definitely no tourists there. It's a place where no taxi driver wants to pick you up, right? And it doesn't matter that it stinks of sewage there, because who cares? So, but the Embarcadero, where it maybe stinks 100 times or 1,000 times less, it's much more sensitive. So it's a different problem to get a grab on, because it's not only about technology. It's also about perception, how people feel about it. So back to the sewers, and as was also mentioned just before, sewers are pretty complicated, and in order to get a grip on what happens in them, I mean, you need somehow some tools to help you along. And here comes process modeling of the sewer networks along as a very nice tool to help you understand what happens in your sewer systems, to keep track of all these chemical and biological processes. So first of all, you have thousands and thousands of pipes to keep track of. That's difficult. You have really, really many processes which interacts and so on. You need to keep track of that. And to do that without a model is a bit tough, at least if you want to do a whole city. So this also meant that from very early beginnings, already back in the late 40s, 1940s, there was the first approaches to try to do some sort of modeling. The first models were risk models, which took the slope and how much water was in the sewers and temperature and such things into account, and gave you some risk to say that in this area you probably will have problems, in this area you probably will not have problems. Later on, in the 70s, as knowledge increased on what actually happened in these systems, empirical models started to pop up, allowing you, for example, to predict sulfide formation in a force main and to predict some level of corrosion. This was mainly work done in the US and in Australia. They were driving the work at this time. Then in the late 90s, we started, we had done a lot of work in Aalborg, and we developed what is called the water sewer process concept, which is a understanding of processes in sewer networks. So it's a way of thinking sewer processes. For those of you who have been working with activated sludge models, it's similar to, you have a way of thinking how things happen in a treatment plant. In the same way, you need to have a way of thinking about how things happen in the sewer network. I'll come back to that. With a model like this, you can simulate whole cities. I already showed some examples. These are some newer examples with some better graphics in them, where you, for example, see the city of Aarhus here, which is 400,000 inhabitants. With the blue lines are force main, the green lines are gravity mains, and the red lines are pipes with more than 1 ppm of hydrogen sulfide in the sewer. On the right, you see the same thing for San Francisco. So you can do whole cities. If you have a hydraulic model set up, it's not super complex. Of course, it takes some work, but it's definitely doable to set it up within a reasonable budget. And it really helps you getting a better overview. This is Aarhus again in Denmark. So if you, for example, zoom in on some outlying village here, you can see here that these red pipes, they all have corrosion rates more than 10 millimeters per 100 years. The number is just arbitrary, just something I coded in to show, right? But this would then tell the utility when they should start inspecting sewer pipes. These are the pipes they should start inspecting in order to prioritize the work on the maintenance of the system. So it helps you really get a grip on the complexity and prioritizing your money and what to do. So what does WATS cover? It covers all the relevant biological processes, aerobic processes, meaning oxygen is present, what happens there. It does all the stuff like degradation of COD, of organic matter, oxidation of sulfide and whatnot. Anaerobic transformations when nitrate is present, and anaerobic transformations when you form the sulfides, mercaptanes, because not all that smells in sewers is sulfide, and also methane, which in some networks can be pretty critical. It covers all the chemical processes, chemical oxidation of sulfide, for example, but could also be other stuff, precipitation with metals, liquid gas mass transfer. I mean, when you have a problem, when you're modeling what happens in the sewer, you need to model both the water and the gas, because as long as the stuff stays in the sewage, it's not a problem. It first becomes a problem when it goes into the gas. So you need to simulate the water phase, the gas phase too, and you also need to be able to simulate the pH, because especially for hydrogen sulfide, you need to know the pH, because the transport of H2S across the water gas boundary is determined by pH. You need to do your hydraulics, so you need to route your water through the network, and in WATS it's done as a semi-steady state, non-uniform flow, meaning you can calculate backwaters and stemming up of waters and stuff like that. And you can also do diurnal simulations, etc., etc. It routes the gas, the sewer air through the network, and it simulates the release of sewer air to the urban atmosphere. It can do all management solutions. Everything on the market is in there, I would say, and then you can do the whole bunch. Oops. It also does stochastic modeling for extreme event statistics and sensitivity analysis, which often comes in handy. All this is done by solving a large number of partial differential equations. I love mathematics. I love differential equations. I love crunching them. And this sounds and looks, when you look at the equations, it looks really complicated, but it's not really that difficult once you learn how to address it. And the approach is similar to what is known from activated sludge models, meaning the way the equations are formed, the biomass is in the center of the processes, etc. It's similar to what happens in anaerobic digesters. Actually, the pH model in the WATS model is a model that is taken from anaerobic digesters for calculating pH, and similar engineering process models. This is just to scare people. It's not because you're supposed to read it, it's just to scare you, so that you can see some of the complexity, some of the mathematics which is inside the model. To show what the level the model does it on, it calculates everything typically on a meters resolution. You can also do finer resolution if you want, but it's normally not needed. It, for example, calculates the water. Like here, you have this negative sloping pipe. You have some backwater, and such backwater creates problems because the oxygen will be depleted when it's partway into the backwater, and when the oxygen gets depleted, hydrogen sulfide increases, it rises up, and then it becomes aerobic again because oxygen comes into the water, and this is partly due to stripping of H2S to the sewer air, and partly due to oxygen coming into the water and oxidizing hydrogen sulfide in the water and in the biofilms. So all these things is covered meter by meter by meter in the model. This is another example. This is from Stockholm in Sweden. This is a force main which is about what is it, 700 meters long. It creates quite a lot of sulfide, approximately 10 milligrams per liter on a warm summer day. It goes into a gravity main, and then the sulfide slowly disappears over the next kilometer or two. If you look into more details in this, what you can see up here in the top, the blue line is the last part of the force main, and the color coding you see here is the corrosion rate. So red means really bad, and yellow means bad, right? You can also see down here you have the numbers. You see at the discharge point you have about 3 millimeters of concrete corrosion per year. So that's quite a lot. So this is valuable for the operators, because they will say that, okay, this piece of pipe here that is here in the green area, if it collapses, yeah, okay, of course a little bit bad, but I mean it's easy to replace. But if it collapses under this 4-lane road, you really have a problem. So this will definitely prioritize where you put your efforts, right? So this is what you can use it for, to one amongst others, to figure out what to do. You can also figure out prevention strategies and so on. So you can also identify solutions. You can calculate how much would you have to add of iron or nitrate, or a mix of them, or whatnot, in order to manage the problems. Next, we also have another part of the model, which is called megavent. And this is a totally physical model. It solves the momentum balance of the airflow, and it yields the pressure and air velocities in all pipes. So if you think about the manhole covers you saw with all the holes in it, when you know the size of these holes in the manhole covers, and you know that in all your system, you can predict from the physics of the airflow, you can predict pressure and velocities. And why do you want that? You want that because you typically have big cities. So this is a part of Aarhus, and this street here is this street up here, and it has severe odor problems. Why? Because gas is coming out of the network. It should not. The model says it should not. So actually, there's something happening which we do not know about. But that's another story. So what you can do is you can calculate the pressures. Here you see the pressures of the network. If you have natural ventilation, so it's in slight negative pressure. If you put forced ventilation on it, if you suck air out at some location, you then also can predict what the pressure is. So this is very helpful. Again, like when you have a model like this, you can run it uncalibrated and you get some rough ideas, but it's of course much better to calibrate it with data and get some real validated data. But that holds true for any model, whatever you do, and also here. You can use an approach like this to forecast the future. This is intended as climate change. For example, what would happen if the temperature was increasing? I think this is data from the UK, if I remember right, where I also do a lot of modeling, looking at how temperature affects the formation rate. Or you could look at like the case we also saw from Germany, where water consumption is being reduced due to people using less and less water, right? So using less and less water is of course good for the groundwater, but it's really bad for the sewers, because you see, as you use less and less water, you get more and more sulfide in the city. And this is this you can simulate with these models to a whatever level of zoom you want to do this in. You can do a lot of more stuff, of course. and I could sit here and then talk for days about this, but then you probably fall asleep. So I will not. Thank you.
Thank you, Professor Holston. So
I heard it the second time today. As we have already had a meeting today this morning, and as you can see, I didn't fall asleep.
yeah.
So
you did a good job, Professor.
No, I mean from every presentation I heard, you learned 10%. So now I have to listen to you 7 more times.
No, it's not accumulative.
Yeah,
you know, you did easy.
Yeah, I know. Why are you doing that? Why are you doing that? Yes.
Processes.
I'm always 10%, like a computer, you know, like downloading. So it's very interesting every time, and you learn a little bit every time. And thank you so much.
Thank you so much, Professor, for your presentation and your time. Does anyone have any questions to the professor or to my presentation or to the model which I explained first of all? And okay, and Isa, you said you are from Morocco, right? So
yes, we are from Morocco.
So what Professor said, is it still a problem there? I mean, what is the present situation in the area? You have any idea what's going on there? Like, is still having a problems, or what are they doing, like a solution there?
Okay, so Professor presented, I think, Tangier. This is it is a big city in Morocco. So I was working in the region of Casablanca. It's similar, but we still have problems actually. What this sulfide problem is a huge problem in Morocco as well. It's like we have unfortunately tragic accidents. The personnel of like cleaning, some of them died because of this sulfide, and yeah, it's really sad. But the problem is in Morocco, we how can I say, we measured the sulfide concentration in the network, but there is, I think, no modeling of the sulfide distribution in the network, and this is really interesting stuff. So we know, as the professor said, where is the corroded areas where you can like where you can like put your intervention, so you can change the pipes and the
under the surface lines.
Yeah, exactly. So I've just like a quick question for Professor, because he was presenting something really interesting, the modeling and all of this. Can we like use the precipitation in favor of cleaning the sewers and the reducing the concentrations of sulfide? Can we like use it in a way so we can optimize like this sulfide reducing stuff? Thank you so much.
You meaning the flushing of sewers, basically?
Yeah, exactly. Yeah. Yes.
I mean, when you have a nice sewer which is always self-cleansing and never has sediments, you of course have much lesser problems, but it's not always the case, right? So when you get these very shallow sewers, you basically get something which is like an anaerobic fermenter, like in a treatment plant, and your problems can be huge. I had a case in Denmark where they were, even in Denmark where it's pretty cold, right, where they were above 5 to 10% methane. So meaning they wanted to renovate the thing, and then they got scared, because if a piece of iron hits the manhole cover, the whole thing can say kaboom, right?
Yeah, collapse.
Yeah. So sediments, especially when you have a siphon or very big, far too big pipes, which are with still standing water, flushing can definitely help, but you have to do it a lot. But it definitely can help, and it's one of the high risk structures to have these cases. I mean, but unfortunately, there is no magic bullet. So I think there's only hard work, and yeah. But I recognize the problem you tell about that. It's definitely.
Thank you so much. I have my friend here. He has a quick question as well, if you may.
Yeah. Hi. I'm Usam. I'm also from Morocco, and I was working also in the sewage system, designing them. There was like in the last time I worked on a project in Morocco, I remember that there was new legislation saying that there shouldn't be any aeration holes in the
manholes, you mean?
in the manhole. Yeah.
Yes.
But
Okay.
yeah, I remember one time it exploded, as you said, because of the gas. But I think that solution only like prevented people from smelling it, but the problem is still there.
It's if you seal your manholes,
Yeah.
exactly as you say, the problem is still there. It might even increase, right? But if you seal your manhole, of course, there comes no odor out of that manhole. But with the air, the water goes up and down, and it puts pressure on the air. So and the air has to go in and out. So it will find other ways, and especially older parts of the cities which do not have well ventilated sewers. In modern house would have a ventilation up over the roof and stuff like that. Older houses do not. So what happens is that the ventilation happens inside the house instead, and that's not better than having it out in the street, right? So I think just saying that you should not have ventilation holes in the manhole covers is not the solution. You have to look at the whole system in order to find the best way of solving it.
Especially, we found out that if you close up some manholes in the middle, there's a whole area where you have the ventilation of the odors, and if you close down some manholes in the middle, then it might even increase the ventilation. If you have like a street falling down like this, then you have like a chimney between two manholes. If you close down the middle one, then you have the chimney between two manholes that have an even higher chimney height. And then you have more ventilation and even sometimes more odors outside somehow.
Yeah, you have to be very careful when you work with sewer. It's not easily predicted, and that was also why we built this momentum model for the pressure, because it's actually difficult to predict. And it's also, but it's unfortunately also difficult to know your boundary conditions. So,
I mean, there are also other ways, Professor. Like I was researching about this topic, and I found like some useful abstracts. Like there are like some people saying you can use iron-rich drinking water treatment, sludge, into the sewers, which will be like better than the iron which we are adding nowadays, like iron salts or something. So
I'm not sure it's not sure it's better, but it's cheaper.
It is cheaper, of course.
I know that they have been working on Albuquerque in New Mexico.
Yeah.
And there one of the solutions was actually to dose the sludge from the drinking water plant into the sewer network. Yes. And that worked well. And the thing was that the drinking water plant was located well compared to where you need to put the stuff, right? And that worked. That worked. So yeah, you can do it, and if you get lucky, you get treatment for free. But again, I mean, you cannot always make it work. But in principle, yes.
Yes, I mean, okay. So anybody has any questions?
May I ask a question, Professor? I just wondering that nowadays softwares like SewerGems or other business softwares, they have these modules to check and predict the sulfide, or no, up to now, I mean.
Sorry, I didn't. How could you
can you repeat the question, or just?
Yeah, for sure. I'm wondering that the softwares that design sewer networks like SewerGems, that is familiar, I mean, popular in Iran for example, designing sewer networks. I'm not sure that what's happening. In these softwares, do we have any modules to check and predict this sulfide gas and something like that?
No, I mean, the only commercial software other than dedicated software that I know about which has some sort of sulfide prediction is MikeUrban, the hydrodynamic model MikeUrban. But honestly, I don't think it functions. I don't think it works. It's my GERM is a Danish product, so it's I know it pretty well, but I don't think the sulfide model that works. So I would say no. But on the other hand, once you have your pipe network in the form you can export it, it's easy to pull it into a model. So establishing the link, if your quality of your data, meaning the pipes and the nodes and so on, is good, that's actually rather easy. So when we do a new project, we try to assess how good quality the hydraulic model is, because if it's just yes, then it takes only some hours or now maybe, but it doesn't take long, right? A few days, and then you have it in. But if you have to do quality check on all the pipes and to figure out, because this pipe, is it really there or is it not there? Does it have the right diameter? Then of course it's difficult.
My second question is that in combined sewer networks that collects rainwater and sewage too, as these networks have less problems. I mean, based on your case studies, because they are bigger and something like that.
Yes, in general, the Northern European networks, because they were combined systems, originally had less problems, also because the sediments were flushed away and so on. But what happens now, sort of, is that we changed to separate systems, and then sometimes these old combined sewers got turned into separate sewers. So you keep the old infrastructure, but only have the wastewater in it, and then you get much bigger system problems, right? Because you didn't quite do the whole refurbishing of the system. But yes, but in principle you're right. Yes.
Thank you.
Yeah, in the mixed systems, you mean the wastewater precipitation helps the, I mean, has less sulfur than the separate system.
And what happens in a mixed system is that you typically have very low water levels in the gravity tubes.
Yeah.
So you have a higher reaeration.
Yeah.
So if you have a separate system, especially if it's a bit older, you might have a half full flowing pipe or more, like you saw the pictures actually from Tangier, Morocco.
Mm-hmm.
And then you get this very deep water layers, and then you get more problems.
Yeah.
So it's everything depends on how the systems are designed, but yeah.
And excuse me, and the problem in the summer is worse than other seasons. Yeah, I mean, in this combined system, they can work better because in the summer we do not have any rain and something like that.
Yeah, I think it probably again depends on the region. But if I take Northern Europe, it's in the summer it's warm and dry. So you have higher temperature and you have less diluted water because you have less infiltration inflow. In the winter, you have lots of groundwater seeping into the sewer, so you have much more water. It's thinner and it's colder. So residence times in winter are shorter, with more diluted wastewater, with colder wastewater, and all these factors together then cause less problems. So it's not only the temperature, but it's also really about the dilution of the wastewater.
Thank you.
And in the Middle East, it's due to the temperature, the hydrogen sulfide explodes sometimes. I mean, because of the temperature. So it also depends upon the region, as Professor said. And yes, so I have one last thing to show you guys. So who is coming to IFAD in Munich this year? Anyone in the group is coming to IFAD?
Maybe I can go there. Yeah.
Okay, so yeah, if you are coming, you can visit our stand, and we also have. You should visit the stand, and we have a stand in this IFAD, which is happening, like it happens twice every 2 years once. So this time we are having it there, and we also have a special episode. And who is interested, please can come next month on 2nd of June. So we'll have a live discussion, and we see what's going on in the IFAT and what's the, it's like a, it's in the terms of saying it's like a Coachella for wastewater treatment people in Europe. It's like the huge festival, and you can meet like everybody, literally everybody in water and wastewater treatment there. So if you please do join the next month, special episode from IFAT. And if you are in IFAT, please do visit our stand, and we have a special for you guys. So if anybody wants any more like this presentation in the email, please do write in the chat box your email so that we can send you this presentation from me and from Professor as well, if it's okay. Then yeah. So if there are no further questions, I think so I guess this is it. And thank you all for joining, and thanks, Professor, for coming as a guest host for the second time. I know you are on your way, and you still manage it from your car and from your going in the road, and then see, that's technology.
I'm not driving. I'm not driving.
Yes, I was making sure of it, because if you're driving, I would say no. I don't want to risk a life for the for this presentation. So yeah, like I said, this is technology. Like a few years before, it's not possible, but now everything is possible. So thanks again, everyone, and have a nice evening. And like I said, please write your email address if you want the presentation. Bye-bye, and have a nice evening. Bye-bye.
Bye-bye.
Thank you so much. Bye-bye.
Bye.
Bye.
See you, Pat. Bye.
Thanks.